what we're looking at here is here's a big vector space. Essentially this is R3C. We have the zero space here. So we know this is a vector space. We know this one is, we know, look at all the subspaces. These are like different lines. These are different planes. So this, and we're going to see that any vector space is composed of lots of vector spaces as subspaces, and they're all flat. It's just like saying, okay, in 3 space, we've got all kinds of lines and planes, and the lines and planes fill all the possible flat structures that are unrestricted. Okay, so the kinds of problems we want to look at are those that are on Rig X. So let's look at some of those. Then you get something concrete. Okay. So then there's some information about the different examples. Euclidean vectors. Well, here's one. Consider the Euclidean vector, line segment with an arrowhead from the point with coordinates here to here. What's the canonical representation? I don't know if these page numbers are accurate anymore because this might be for a previous version of the text. But it's what we went over in this chapter, okay? Canonical name, polynomial, okay. Suppose that V equals W with these vectors, members of P2, with V equals this and W equals this. What's A, B, and C, okay? That's just a test. Here's some vector arithmetic. Adding 2 polynomial vectors. Here's adding two matrices thought of as vectors. The zero vector. Okay, here's the question. Consider this equation as an equality of vectors. 3 plus 3x equals 0. In this context, what can we say about this equation? It must be that x equals -1. The equation is false. We don't have enough information to affirm either of these responses. Suppose that this equation is true as an equality of vectors in P2, a minus b, x equals 0. In this context, it must be that x equals a over b, a equals 0, and b equals 0. We don't have enough information, okay? The last one is decide if the following points lie on the line. Okay, so I give you a series of points here. And the question is, do they lie along the line through these 2 points? Well, that's the problem we did earlier, right? When you want to find there's a point on a line, you take the difference of these 2 vectors, right? This might actually be the same problem. Except for the fact that I'm giving you 4 different questions is, are these 4 things, like that? Well, that's what we've already done. So, let's see. There's a definition. Okay, so here's one of these. We want to say, I'm giving you a list of these, sort of logical steps, proof steps. So you have to sort of become familiar with these things, and it's sort of like saying, consider this subset of a vector space. Okay, here's this definition. Is this subset also a vector space? If so, then it is a subspace of R3. Here's a verification which appeals to the subspace test theorem. That's the one we just looked at. This means we're appealing to the result that if the vector T is an arbitrary, if the linear combination T is an arbitrary linear combination of vectors in S, and T is a member of S, then S is a subspace. So we're going to say, okay, we know that T is a member of S, and T is an arbitrary linear combination of vectors in S. Then we want to say then S is a subspace. Okay, so here are 9 justifications, and then it is, let's see what, and I want to show that this is a subspace, right? So it says, let R and S be arbitrary real numbers, let these be any vectors, and it goes through one of these things that will verify that the arbitrary linear combination is a subset, but doing it with baby steps. Let's see. I go through this verification with polynomial vectors, with matrix vectors, and then we come to the topic we haven't come to, which are spans. Okay, so I think that you have the facilities now to deal with about 2/3 of the problems on regex that are the sort of, you want to go through and do those just to sort of firm up that you've understood this stuff. And I think you'll see you don't have an infinite number of choices. So don't use them all up. And if you get to number 4 and they're still wrong, then come and talk to me so we can get them right. Okay, so we're sort of out of time. So I think we'll stop